Bam, Mr. G here. Alright guys, so today we're going to be talking about Hardy-Weinberg equilibrium. Now what Hardy-Weinberg equilibrium is a situation that states that allele frequencies do not change over generations in a population, and we can use these allele frequencies to predict genotype frequencies in the future. So here are the 5 principles of Hardy-Weinberg. The first one is random mating. In order to follow Hardy-Weinberg equilibrium, a population has to be going through random mating, so there can't be any selective breeding, which is the choosing of individuals to mate with each other. The second is no genetic drift, so this means that there can't be any fluctuations in allele frequencies inside a population. The third is no gene flow, which means that organisms and populations can't flow in and out or leave populations because this would disrupt the allele frequencies in that population. The fourth is no mutations, so no mutations can occur while going through Hardy-Weinberg because, it would disrupt the allele frequency in a gene pool. Lastly, no natural selection can occur. So organisms with all genotypes, it doesn't matter, they all go through the same living and death. So it doesn't matter, there's no perks, there's no adaptations that go on. So everything is the same. So in order for Hardy-Weinberg equilibrium to work, all these must be followed. So this here is the Hardy-Weinberg equilibrium equation. Now this side is used to find allele frequencies for the dominant and the recessive trait. This is a quantity of p plus q squared. Now the p represents your dominant allele frequency, while your q represents the recessive allele frequency. On this side of the equation we have p squared plus 2pq plus q squared. Now this side is used to find your genotype frequencies inside a population. P squared stands for the homozygous dominant allele. 2pq stands for your heterozygous, and q squared stands for your homozygous recessive allele. Okay, so generally when you're solving Hardy-Weinberg problems, you want to find your q squared first, or your homozygous recessive genotype. The reason you want to do this is, in an equation, you know that, let's have an example. Let's say there's a population with the brown eyes being the dominant trait, and green eyes being the recessive trait. Well, even if they give you the amount of people with brown eyes, you don't know which are heterozygous and which are homozygous dominant. But if you know that a certain amount have green eyes, then you know all those have the homozygous recessive trait. So your first step is to find that. So after you find your q, you're going to want to square root it. So you have your q squared here. And the reason we square root it is to find the q value. And remember the q value is the frequency of the q allele, of the recessive allele. So once you have that, you can find your frequency of p alleles, or homozygous dominant alleles, because we use this equation right here, p plus q equals 1. So once we find this, we can just move the 1 over, and we have p equals 1 minus q. Now this is going to help us find our p value. Now once we do this, we're going to have both our p and q values, so we're going to have the frequency of the p allele and the q allele. So once we do this, we can now find all of the genotype frequencies, because all we have to do is plug it in. Once we have our p, we square it, and we get our dominant, our homozygous dominant genotype. We use our 2, and we also substitute in p and q, and we get our heterozygous, and we substitute in q, we square it, and we get our homozygous recessive genotype.
So today for the first problem we have, sometimes you start off with the genotypes and want to get your way to the allele frequencies. So in a population, there are 90 people with brown eyes for dominant homozygous, 40 people with brown eyes for heterozygous, and 70 people with blue eyes for recessive homozygous. Find the values of p and q. So these two equations are the ones you would use to find the values of p and q. You'd use 2 times the number of dominant homozygous plus the number of heterozygous over 2 times the whole number of the population. So for the value of p, we would have 2 times 90 plus 40 over 2 times the entire population, so it's 90 plus 40 plus 70. So overall we have 180 plus 40 over 2 times 20. The value given is 0.55 once you plug into the calculator. The next thing we have to find is the value of q, which is 2 times the recessive homozygous plus heterozygous over 2 times the entire population. So for Q, we have Q equals 2 times 70 plus 40 over 2 times the same number here, so it's 20. And we have 140 plus 40 over 400. And this equals 0.45. To check your answer, you have to make sure these two equal 1.